Cool. So I'm happy to announce our last chapter in this book club. Rewriting R code in C++. So why do we want to do this? Sometimes R code just isn't fast enough, and C++ can address several points where we can improve R code, or where we can make it faster and just improve it. And some of those points are that loops that can't be easily vectorized because subsequent iterations depend on previous ones. And I think also generally loops are somehow faster in C++ because they don't use so much overhead, whatever that means. Also, recursive functions are apparently good to write them in C++ instead of R. And if you have problems that require advanced data structures in the algorithms that R doesn't provide, C++ is also a good alternative. And we can use for that this package called Rcpp, from which we can basically in R also write C++ functions. So to get started with C++, for me, this was really, really new. I've never touched this topic before. So I'm happy that I was able to at least get some of it and was able to read it more or less. It was a nice introduction in this chapter, the functions. So this is just a very simple C++ function, and you can use this R function, which is CPP function from, I guess it's from the Rcpp package, and then write within this function some C++ code that looks like this. And then basically you can use this function. So in this line, you define the name of the function, which in this case is add. You tell that the output should be an integer, and you declare the inputs that should also be all integers. And then just say you want to declare a sum that is also an integer, and this is just the sum of all those three inputs. Then you return the sum. And afterwards, you can just simply call this function that's now called add in R, like a normal R function. So add 1, 2, 3 would then result in 6. Here, basically, we go again through a bit more simple examples. So how to translate actually an R function, which is really simple. So this one is just a function that returns 1. And the C++ function, the corresponding one, would be, again, telling you, or you have to tell in this function, declare the output type. So in this case, an integer, the name of the function, and then this function does just return 1. And so this is just a really important point that is different from how you would do it in R. You have to always declare the type of the output the function returns. So for vectors, it would be numeric vector, integer vector, character vector, and logical vector. And you have to do this also if you just have scalars. And then it would be double int, string, and bool. And you always have to explicitly return, use a return statement in order to return a certain value at the end of the function. And every statement is terminated by a semicolon. And similarly to declaring always the output, you also have to declare the input. So this is just, I cut off the rest of the function here just to show this point, that you have to also declare the input in the same way. And one point, apparently it's okay to use loops in C++. So when you go to C++, you can start thinking again in loops. And here we have basically a function again in R. So how we could write the sum function in with the loop in R would be we have an input x, and we go through this vector x, and always add in each iteration the value of x at I to the total value and return a total. And we can do exactly the same thing in C++, where we again declare the output, which would be a double, and the input would be a numeric vector. We say in the beginning that n would be basically the length of x. We set an initial value for the total, which is 0. Then we go through the loop. We have in the for loop here, we have 3 different points that we have to set. So it would be the initial value I, and then it's always checking the condition. If as long as I is less than n, it will continue, and it will add 1 plus to the I at the end of each loop. So with the plus plus, you just always add 1. And in each loop, you increase the total by the value of x at I, and in the end, you return the total. So there are some things that are a bit different to R code, and some things like this plus equals that I guess are quite handy to use, or the plus plus. You can write a little bit less. One more important point is that in C++, vector indices start at 0, so not at 1 as in R, but at 0, which also means that the last element is at the position n-1. And this is probably something, or yeah, it is something that very commonly leads to bugs when you think in R and you start working in C++, for example. And we can also compare these 3 functions now, the base sum function, sum C, and sum in R. And we see that at least those 2 are really different. So the for loop that we wrote in R is much, much slower than the for loop that we wrote in C++, but still the base R function is a bit faster than the C function. Yeah, okay, so, and also instead of using this function, what was it? CPP function, you can also use source CPP to have some standalone C++ files and then just source them in R. And I also realized that you can basically use this in a R Markdown chunk if you declare in the chunk options that you use Rcpp instead of R. So that's quite cool. You always have to include this special start here. So these 2 lines in the beginning, and then before the function that you want to export, you need this line. Then you can just write your function. In this case, it's the function for mean. And you can also include embed R code in these C++ standalone files if you include this line before the R code that is embedded. Exercises. So in this part, I just included some of the first exercise. I don't know if you did any of those. I found them was quite interesting. So read the code and figure out what the corresponding base R function is. Like a little quiz. So the first one was still relatively easy, I think. So in this function, we return a double. We have an input of a numeric vector, and we first again declare the size of the vector, then the initial value y, and we always increase, like we loop over x, and we increase in each loop y by the value of x at I divided by n, and then return y. Did you do these?
Yeah, some of them, like, I didn't know, I had never heard of the R function before. So it was F4 and F5. I had no idea what base R function they were referring to. I was like, what is this?
I had the same problem. Yeah. This one I still knew.
Yeah, this one's easy.
This is the mean.
Yeah.
So yeah, it works even a little bit faster. I was a bit, because I think I would have done it differently in R. I would have like made the sum of all the x's and then divided by n. But yeah, it also makes totally sense like this. That's nice. Yeah. The second one. So you get an output of a numeric vector. The input is also a numeric vector. And in the loop, so you start by declaring, or you create an out numeric vector of the same length as the input vector. And the first element of out is the first element of x. You go through the loop and you always add, or you create a new element in out, which is the element that is at I minus 1 in out plus the element that is at I in x, and then you return out. I think this was also still okay. So that's the cumulative sum. Mm-hmm. And this is, though, not really faster. I just checked it for fun. It's actually slower than the base R function. Number 3. This I also had a little bit of problems puzzling it out because it looks somehow different, but I think I figured it out in the end. So you get a bool value out. You have an input of a logical vector. And so the thing where I was a bit struggling was here in this if. So if the value of x at I is true, you return true. And then you have, after the for loop, the return false. But I think in R, you would actually have it like as an else statement, right?
Well, so I think it's saying that if none of them have returned true, because if it returns true, then it would break out of the function, I think. And so it's not an else because it's not on a case-by-case basis. It's across all of them. If nothing's returned anything yet, then it will return false.
Okay. So if one value is true, you return true. Yeah. And if it's false, it's keeping in the loop. And if none of them return true, you return false.
Yeah.
That makes sense. Yeah. So that's the any. And I tried it out with three different vectors, so it works as any. But it's also a bit slower than the base any. Yeah, I think this one was also, I didn't know position. So I also didn't really know how that works. I don't know if you...
I guessed map. I was like, is it map? Like, what is this one supposed to be? And then I had to look at the answers. I was like, oh, I guess it's position, which I had never heard of before.
Yeah, me neither. And I was really confused because you have as an input a function and a list. So, and then, yeah, I really, I don't get it really. Because then you have, you create a logical vector and you call the function with the value at I of x. And if this value is no.
Okay,
So you also didn't.
Okay, so you make a logical vector, which is going to be, oh gosh, yeah.
But this function can be any function.
Yeah.
You can use it. Okay.
I mean, position, if you read the R code for it, gives the first or last such element and its position in the vector respectively.
Yeah.
Huh.
I think I even, oh, no, I didn't.
Oh yeah, pmin as well was the other one that I was like, what is that?
Yeah. Oops. Yeah, find and position give the first or last such element and its position in the vector respectively. Well, okay. So I'm not alone. That's good. I don't know, did you check out the solutions for that? I have it here. They just write its position, okay. They don't really write how it works.
No.
Okay. Well, then that's that. Okay, so we had now, we had vectors and scalars as classes in C++, and there's of course also other classes that we can use here. There are, for example, lists and data frames, and Hadley said that those would actually be more useful for output than for input, because also here you have to always state which type of data you have here in the list or in the data frames, and sometimes you would not maybe know what the input type would be in a list or a data frame. But nevertheless, in the example that he puts, he uses a list as input, and this is basically a function to create the mean percentage error. So your input would be the output of a linear model in R. And you can check first if this really is of the class linear model, I guess, the input. And if not, you just stop the function. Then you declare a numeric vector that's the residuals, and you can just access the residuals from this list by the name. The same goes for the fitted values, and you say this should now be a numeric vector. And then you loop through those, where would you loop through? Yeah, the residuals, so the length of the residuals, and you create, yeah, in this loop, the mean error percentage by dividing the residuals by the fitted plus the residuals, and then return this divided by n. You can also use functions. And in this case, yeah, you would just basically create, this is again really simple C++ function where you have the input object being also a function, and then just call this function with 1. And in this case, because you can use any function here and you would not know what the output would be, you can say that you just catch it in an R object, because then you just cover everything and you can catch anything with the R object. So you can, for example, use this with the function x plus 1, and this would just return 2, because then it's 1 plus 1 is 2. Or you could call this with paste, and you would just paste 1 here as the result. And the next point was about missing values. And here he says that it's important to know how R's missing values behave in C++ scalars, and also how to get and set missing values in vectors. So one example here was just how you would create a list, or how you could create a list of missing values of different classes again. So you can always have to declare the class or the type of your variables. And this would be the output here. So it looks quite okay for the integer, the strings, and the numeric, but not really for the logical. But if you look a bit deeper into it, this is also not necessarily true for the others, that this works. So you should keep in mind that integers, if you create an NA integer in C++, it's actually stored as the smallest integer possible in C++. So if you would use it in a function like NA integer +1, you would get the basically smallest possible value +1. So this is to keep in mind that this might cause problems in sorry, might cause problems in certain situations. And he said doubles, you can actually work easily with NaN. You just have to be careful in combination with Booleans. Strings are no problem because they are actually, so the NA, what was it? String is actually, comes from the Rcpp package if you use it from R and C++. So it's defined in there and doesn't cause any problems. And for Booleans, the problem is that C++ only has true and false, and R has true, false, and NA. So if you have an A and you want to introduce it from R into C++, they will be coerced to true. So this is the problem that we saw before. Yeah, you just get true. And for vectors, you have to, again, use this combination. So NA real, NA integer, logical, and string.
It's so weird to me that NA gets coerced to true. Like in my head, it should be false. That's what it should be. I don't know why. That's weird.
Yeah, but maybe because false is 0 and true is 1, and NA, I don't know, is not 0, but I don't know. It's weird. I also don't know, he didn't say anything like how you could handle that, right? In the book, how you could circumvent it.
I think it was just like be aware when you're like trying to build stuff later and you're getting odd bugs. Like these are the things that could lead to your bugs.
I think the solution was to convert it to a numeric with 1 0, and then it can do NaNs.
Yeah, true. For the bool, yeah. Because then you have so it would be integer again, or it would be
yes, probably double. Assuming it can do well, yeah, doubles can do NaN, but maybe integers if they can do, but then they store it as the low number, but then that still distinguishes it, doesn't it? So.
Yeah. Okay. So there was this exercise. I started doing it, and then I realized I don't know really how to do it. I don't know if you did any of those, or if you want to do one together. So rewrite any of the functions from the first exercise to deal with missing values. If NA remove is true, ignore the missing values. If NA remove is false, return a missing value. If the input contains any missing values.
The only one I tried from exercise 1 was all. I redid that one, so we could try and do it now and give it NAS. Here, I just put it in the chat. It's pretty short.
Okay. I can copy. Where do I have this?
Oh my gosh, I'm not even sure how. I didn't do the whole thing though. Oh, wait.
Did you do it in or did you just do it in an extra script then?
Yeah, I just said it in an extra script. Okay, how do we deal with NAs?
Oops. So this was
This
one
is
from
just
me.
yeah. This is from exercise 1, just without the dealing with NAs.
Ah, okay.
So do we have to check for the like loop through in the loop and then check if any of them is a NA first?
I guess.
Yeah. Well, because what's the thing? It's like if remove NA is true, do something. If it's false, do something else.
Yeah, if
ignore the values. If it's false, return a missing value. What do you mean return a missing value?
Like, I guess return NA logical.
Because if you have
like a value for
false,
it, yeah.
And you have some in there, you would return NA because it's
sure. Okay. So we'll need the NARM argument, and then you can have the in the loop, it can be like, firstly, if it's true or false.
Yep.
And then if it's true, it kind of ignore the missing values.
Wait, that was.
God, my brain is so slow today.
The bool logical.
So I think that's the one we'd want to use.
But inside of the for loop, or?
I think we have to.
So this is.
We have to use this, and I think we also have to return this. So I think this is what we want to output if anything is a nah. And I think we also want to check for this.
Yeah. So first we will also need this NA remove. Which
and we
is
have to
bool, yeah.
And so we would check first if NA remove is true or false. Right. So if and what do we do if so if NA remove is true, ignore the missing values. So we would.
So we can do it inside the loop, right? So it would be, I think, our second line inside the loop. So if NA remove. Yeah, one down. Yeah, if NA remove. If NA remove, and then we have to check.
We ignore the missing values. So we would have to remove them because otherwise we will have.
Maybe something like if NA remove and XI equals NA logical next, something like that, which would just skip it. I don't know what the C++ next is though.
They had something, it was like, there was one thing that was different. One thing was like continue and one thing was like,
yeah.
Let's find that.
So XI.
Continue instead of next to skip one iteration.
Can we use like is NA or something like that?
I think it's an R function. I think we have to test. I think we have to text X of I equals NA logical.
Is it logical or was it bool?
Or is it because we're feeding it
logical.
We're feeding it a logical.
Capital letters. Oof.
Okay, so if NA remove and I think we need one more.
Yeah.
Yeah.
And then
we just continue.
Yeah.
Which would go to the next iteration of the for loop.
Yeah. Continue and then semicolon because it's C++.
Yeah.
Sorry, the semicolon, yeah.
Yep.
Yeah.
Did you ever do anything in C++ before?
No.
Just teeny tiny, okay. Good.
Okay, continue. And then otherwise it should work, right? And then we need to check for if NA
false.
remove is false.
So then we have continue, and then we just continue with the next if statement. And
oh, I guess we should do it differently, shouldn't we? We should have a big test for if
in the beginning,
isn't,
right?
yeah, if xi is illogical. Wait, sorry. Okay, so wait, we can do it like, I'm gonna type like first we check. I just typed the same thing. So first we check if is NA, and then we have under that if NA remove continue, else return nah logical, right? Because it should, if we have anything that is a nah, we should return a nah logical. So on line 26, we first check.
Okay, yeah.
But here we have like an A remove is true.
Yeah,
so
but we have
them.
Yeah, but we should have basically two options under each. Yeah. Sorry, wait, I type. I'm not explaining myself well. It is hard to speak. If NA, so
it's like if xi equals NA logical.
Yeah.
And then it's if NARM continue or else return logical.
Yeah. Yes.
So
these are the
outside. So we first check this.
Starting with that one. And then we have another if statement. How do you?
I think.
But it's only but then we first have to also check if if NA remove is.
So that can be next. So like if it's logical, then it will be a check.
I don't know if this works. Let's see.
Yeah, so then after this if NA logical, so there's no continue on that bit. That's just the start of the if statement. Then we have another if statement in there, which is if NARM.
Oh.
I don't know. I don't quite know how it will look in C++, but and then we have continue, else return NA logical, but I don't know whether it's how the lines split up.
You mean so if
yeah.
And then else, but it's not written else, right? It's just.
I think if else is like.
I think you can do if else. Right.
It's so confusing also with the semicolons.
Yeah.
Where to put them and where not. So else return NA. No, false, right? Return false. No, NA.
Yeah, NA logical.
Yeah.
But in all caps, maybe.
Yeah. Okay, so this basically covers both cases for NA remove already, right? So this. And we also need this. We can try. Okay, I really don't know what that now means. Explicit braces to avoid jangling else. So I think the else thingy doesn't work.
Maybe let's put
I think
stuff into
maybe
braces.
curly braces.
Yeah. So like curly braces around line 24 and 25 to show that they belong to the if statement above. Yeah.
Like this.
Yeah, and then possibly curly braces around continue semicolon. I don't know if it's necessary because it's on one line, but just and then around return NA logical.
Okay.
Oh, it's also throwing you a compiler error because of the total 0, but that's not what's causing it. Yay, it compiled. Yay.
What's the double total?
Oh, it's telling us that we shouldn't have done that because we didn't use it. This is like, it's part of why C++ is faster, is it's a little bit more strict about the memory.
Okay, cool.
So it's like, hey, why'd you make me make this stuff? Yeah, it's a warning, not a end of life.
So what was that true? So it would be something like this, and then
yeah, okay, yeah.
All C X and A remove. So this is then like used as a normal R function, so we can use true as
so
false.
So that it's just skipped over the NA. Okay, and so if it's false, it should return NA logical thing. If NA are
but it should return true, right? Because we have some true in there.
No, because if any are false, it returns false.
If any are false.
Yeah.
I thought it's the other way around, if any are true.
Yeah, I think it, yeah.
Okay, it's very confusing.
Because they all need to be true for it to be true.
Because it's not any, yeah, okay. Yeah. So if it would be, maybe.
I think we need to change the return type.
Oh, what?
So on all C, yeah, we don't want to return a Boolean, do we?
Yeah.
Do we?
Well, we might.
Yeah, wait, no, because we want to return false, or we want to turn NA logical.
Yeah, so if we have NA remove false, it should return NA logical.
Yeah.
But it doesn't.
Yeah, it returns true because we're telling it we're returning a bool. Maybe, what if we say our,
is that because we need to change it to like a, yeah.
Okay.
Our object? Is that what it was? Our obj? Rob?
This. Oh no. Oh no. Okay. Okay, 3 errors generated. I'm not sure. Was it our object or?
I think our object. I don't know if it'll work.
Yeah, so our object. That's what
Ooh. I just tried that. I got a lot of errors.
Okay, so maybe
so we don't know what we're doing.
That, we practice a bit more in C++.
I reckon this would have worked if we weren't doing a Boolean thing. If it was something which could return an NA.
Yeah, I am maybe because bool is again. So because maybe you mean this is because it's coercing the NA into C++.
So if we were doing like return an int or something, and
Yeah.
or double, and changed like false to 0 and true to 1, and then was return NA double or whatever I just said, int.
Okay, let's try.
Oh, maybe we have to return a logical vector. I'm cheating and looking at the answers. I think we were almost there. If we change the return type to logical vector.
Oh, so it does does it for each one?
Yeah. But now I also have NA removed true. We have this. NA! Yay!
Great.
Okay.
Great.
So maybe we continue with the last bit.
I mean, I think we nailed that.
Yes, definitely. So the last part was basically about this standard template library, and I looked it up because so in the book it just says basically it's extremely useful, a library that provides data structures and algorithms, and then I checked this other website which basically says the same. It's a library of container classes, algorithms, and iterators. I still couldn't quite grasp what it is, but I guess it's just like we have some sets of data structures that we got to know now already, but there's so many more that are possible to do in C++. And some like really experienced people already constructed those structures, those data structures, and you can find all of them in the standard template library. For example, iterators, which will step up your loops. So they work, basically you then have to define this class as an iterator or structure. And if you have an iterator, you can use this in for loop, for example, and instead of, before we always had to define the length that we want to go through and so on, and now you can just use xbegin and xend and increase the iterator, and then you can also use this asterisk as basically dereferencing. So when you use this, you basically check the position of x or in x of the iterator. So this would be another version of how you can write the sum function using those iterators. Then there's also algorithms that you can use, and he gave the example of find interval. I had to check first what that find interval does, to be honest. I couldn't imagine it. So if you have a vector from 2 to 17 here, and you want to put it into bins, and those are your breaks, basically 5, 10, and 15. The second column would be the output. So 2 to 4 would be the first interval, then 5 to 9 the second, 10 to 14 the third, and then the rest will be the last interval. And so you can use algorithms that are already created in the standard template library. And I also didn't completely understand this function, but I understood that the point is you can use here with std : upper bound or distance, for example. Those are two algorithms that are already optimized, and you can just simply use them in this function for whatever you want to do with this. So not quite sure if I understood it completely, but it does what it's supposed to do. Oh, I have some some things that remind me. So we in this function we step through 2 iterators. So we have here the first, we create them here, the it and pause. So we step and the iterator, iterator, and then the out iterator. So we step through it and out it, and we always increase it and out it after each loop. And one other point here, we can assign into and dereferenced iterator to change the values in out. So in this case, this is here. So we we dereference into out and assign this value to the position in out of the out it in this case. And here upper bound returns an iterator. If we wanted the value of the upper bound, we could dereference it to figure out its location. We use the distance function. So I'm not quite sure what they do, but those are the algorithms that we can use from the standard template library. Then we have some other data structures. We have vectors, and they grow very efficiently here from the STL. And this is very useful when we don't know the size of the output in advance. So the one point, that's always also something that you should think about in R, that if you have a for loop, if you have to use the for loop to define first the output, if you know the size. And in this case, you can just use those. Again, you have to specify the type of the objects, as we learned now already in several other classes and data structures. There's also sets, and they can efficiently tell you if you've seen a value before, which is useful if you have want to do something like unique or duplicated or in. And then we also have maps. And they are similar to sets, but they can also store additional data. And they are useful for functions like table and match. And in those, you have to actually specify type for value and key. So you have to use 2 definitions in here. So this would be the example for the implementation of table. We have an output, which is a map, and a numeric vector, which is the input. This map basically is, we call it counts, and it has values that are double and keys that are like integer. And we just loop through x and then count and increase the number of the count if we find the value of x again. So it's a bit complicated, but so if you have a 2 at the position of xi, you will increase counts at the position of 2 by 1. So you will count it that there is a 2. Hey, and that was it already. So I skipped the case studies. This was even surprising for me. Yay! We did it.
That's very exciting.
That's it.